Hello everyone and welcome to May I AI. In the last episode we talked about affective computing and how AI is able to interpret and detect emotions. In this video we're gonna try to do exactly that. We're gonna, through code, write our own machine learning model that is able to take an image and decide whether the face inside that image is happy, sad, angry, or whatever emotion it is. So let's jump right in. Over here I have a folder with dataset inside it. We have a train folder and a test folder. Usually you would have train, validation, and test, where training is used to train the model, validation is used to validate the training as it goes, and finally testing is used to test the model finally on data that you've never seen before. For now we only have train, and we can always use that to divide into train and validation, but for now we only have train, and inside of these we have all of our emotions that we're going to be detecting, and inside every folder there is a bunch of images. The images are small and they're all grayscale, but the model is going to be able to look into it and decide what this face is. So let's start by writing the class that we need to load the images so that we are able to train with them. So this class is going to be everything we need in order to load the images from the folders that we have into code. This is going to turn them into something called tensors, which we can then use to train our models. So let's go ahead and create a main file that can now read the dataset from using this class from the folder that we have, and then we can also visualize it, but also see how many classes we have for each of the emotions that we have. So over here is the code that we need to write in order to load the data using the classes that we just written in the data loader and data set. And here we're just doing a very basic loop to print the shape of the image. This is going to help us see what kind of output we're getting out of the classes, the data loader, as well as the labels that we're getting. So if I run this, so here we see that we have almost 29,000 images and 7 classes, as we saw in the folder. And we also see that we get this torch here. This is the tensor. And 2 is for the batch size. So you see here that we said that we're going to be loading it in batches. And this is why when you're training, you're usually using a sample of the data sets as you go. So these are called batches. And then we have the image. So 1 here would be the channels. And since this is a grayscale, so it only has 1 channel. And then 48 by 48 is the pixel width and height. And then over here we have a tensor of 2 and 4. This is because we printed both labels here, which means that we have the first label is a 2 and the second label is a 4. Now, the reason why they're in numbers is because the model, the AI, it doesn't really understand text. We cannot really save it as the word angry or happy or whatever. So we always give them the value of numbers. This is also true when we're training on text, that we need to have the values be encoded into a vector. So let's now use the classes that we have and also write code to visualize the number of images per class, as well as look at a sample of images just to see what we're working with. So over here is everything we need in order to load the images, and we're counting the number of classes or the number of images for every class. And this allows us to get an idea on whether or not the data is in balance, if all of the images have the same count, and just gives us an idea on the distribution of the classes for our data set. Running that code, we see this bar plot here, and we can see right away that disgusted as a class has very low numbers. I think we have 400 images for that class, but everything else is closer to 4,000, maybe a bit below 4,000 for surprised. So this is a very clear example for data imbalance, where I assume after we have the models that is trained, the value for disgusted will probably not show as much as every other class. So if we're looking at the confusion matrix where we see the accuracy per class, we will probably should expect a very low value for disgusted. This is something that we should keep in mind. So ideally, when you see something like this is what we talked about in the uh, AI data episode, and we said that when the classes are too low, you would usually need to do something to make sure that the data is more balanced. This includes either finding more values for disgusted or augmenting this, but still for 400 versus 4000, you're going to need to do a lot of work here, that the better option might just be to drop that class entirely, or make sure that you really find new data points or augmented really good that it is closer to the other classes. We also see that for happy we have the most amount of classes here. This will probably be, let's say, the most predominant class, while everything else is going to be almost the same, but disgusted will definitely be very rare to see post training. So now let's move on to the next step that we talked about, which we want to see samples of the dataset. So let's plot two images of every class just to take a look at them. So I've added the needed code here in order to sample just a bunch of images. So in this case, two per class. And we're going to visualize each of those and show them in the same figure. Over here we see a good sample of images for each class, and these are the images that the model is gonna see in order to, let's say, decide if the image is angry, disgusted, fearful, happy, or whatever. And you could see that this is also important to note here, that when you're using the model afterwards, in order to also use it on, let's say, new data points, you need to make sure that the images are the same. So for example, you see that this one, for example, is a bit out of distribution because the face is further away from the camera, but it's also hidden. But if you're using this later on, you would also need to make sure that the screenshot or whatever crop of your face is as close up as these images here. So they'd have to be the same size, and they would also need to have in grayscale and everything that you do. So everything that you do to the image during training is the same thing that you have to make sure you have when the model is in production. So now that we have the images, the next step would be to create the model. Now, ideally, you would use something that is state of the art or a more pre-trained model. Just for the sake of this demo, I'm going to create a model from scratch, and we're going to use that to train. So what I did here is a very bare bone image classifier. Usually you would add more convolutional layers as well as a fully connected layer. But the reason why I did this is I want to also be able to show you how the convolutionals work, so the CNN network, by kind of getting a convolutional, let's say, layer with a small filter size. So it's going to generate another image, and we're going to look at it, and we're going to see how the image changes over time. And this allows us to see the features that the model extracts. Currently, it's going to be a very new model, so the features aren't going to be, let's say, useful, but we can also look at them after training and see how they become more useful to the face and the features within that face. Here is I loaded the CNN that we just created and got back to this loop right here where we use the image in the label. And what we're going to see is we're going to show the images being predicted by the CNN. Now, again, they are not very images, but rather features, but we are showing them as if they were still an image. So we can see that this is the output that the model sees. Now, usually you would show every individual one of these filters on its own, so it wouldn't be an image of three channels, but rather each one of them as its own one channel thing. Also not have a CNN with only three channel outputs would usually be much bigger, but I'm doing this just for the sake of demo. But in this image, for example, you can clearly see some highlights of the face already. You can see some highlights on the eyes, some a little bit on the mouth and nose here, so you can already see that the model is kind of, let's say, seeing some of the expressions or the facial features that make up a face. You can also see it here, although it's a bit different. Currently, like I said, the model here is not trained. So these features here are just the random initialization of the weights and the random initialization of the extractors that don't know what to extract yet. So we're going to look at it again after the model is trained and see how better it has become. So I'll just go ahead and add the rest of the layers now so you can actually have a model that is able to train and predict the number of classes that we have. So I updated the class, so now we actually have the full network. I've went ahead and extracted this feature layer, which we just use this to visualize the model, but we're also gonna look at this at the end to see how better, let's say, they have become at seeing faces at the very early stage of the model. And added this function here so we can call it later. Well, I'm gonna go ahead now and create a trainer class that's gonna take the model in the dataset and train our model on the dataset. Now we have the full training class, and this class just takes the model, the data set that we just created, and it does the training loop. I'm not going to go very details into the training function. I can do that in a different video. But for now, let's train the model and see what happens when it's ready.
One eternity later.
Okay, so the training finally finished, and now what is important to note here is that the loss function actually decreases as we go. So you can see that it started out being at 1.7, and then as we went down, it went down all the way to 1.2. Now it could go even lower. Now usually you would train for 100 epochs, maybe more. It depends on the problem and data set, the model, and everything. For now, I only trained for 20 epochs, which is just to get the demo running. But you could see that the loss keeps going down as you go, and this is a good indicator. Now, usually you would also have the validation loss, and you would monitor both closely. And if the training loss goes down, but the validation loss doesn't go down as much, you would know that there is a difference between the training and the validation data sets, which means that the model is not generalizing to different data points. Now what we can do is use the model that we just trained and try to see if the features are now, let's say, better at detecting stuff. Here I basically redid the code that we had before. I just switched the data to now read from the testing dataset rather than the training dataset. And again, I'm going to show the features. So this is what we had before, but I'm also going to show the individual features. Now, like I said, usually you would have more than three, but for now I only have three. So I will show each individual one of them, and then I'll show all of them on top of each other once again. So let's take a look at how that looks like. So over here we see the output of them. Each one of those is an individual feature map, and then these are the ones put on top of each other. See that for multiple other pictures. And I guess it would be hard to decide what every individual feature map is trying to look for, but conceptually what you would understand is that the feature maps are trying to find features that most relate to how the model sees the input. So the model is looking at each individual one of these and is trying to see the combination of information together in order to find the output at the end. So every time they go on an image, the CNN would kind of look at a context. This is a window of pixels, and try to encapsulate all of the information in that window into one single pixel. And then, as you would imagine, the image will go smaller and smaller, and then these will keep going until only the most important features are kept, but also all of the information on the feature maps from the combinations of features by themselves. So at the very beginning, it would be, let's say, a 4x4 pixel would be into 4x4 grid would be into one pixel. And then now every 4x4 pixel has information from 4x4 inside 4x4. So it will be bigger, and then it will even be bigger. And then all of these will together form what the model sees and how they come to the decision at the end. Let's quickly add also the main input image here so we can look at how that looks like. And there you have it. Here we have the original input image, and then we have the feature maps of what the model sees. If you put them all on top of each other, I guess the green could be interpreted as what the background is, but there's also green here and here. So it's very hard to look at this and decide, this color must means this and this color must mean this, because for now the thing is not an image anymore, like I explained, but rather some mapping to a features within the image. And we can look at a bunch of them and see how different it is from, let's say, beforehand. Great. So now what we could look at next, what everyone is here for, is how does the model see these pictures. So now we're going to look at the image, the input image, the actual label of that image, and we're going to see what the model classifies it as. Great. So over here we have the input image, and this is the actual label of it, and here we have what the model sees plus the prediction of the model. We can see that some of them are predicted correct, some of them are not. Now, as expected, some of them, the model will not be perfect because it wasn't really trained for that long. But you can see that for some of them, the model does manage to predict it properly. What we can do is now look at the actual uh, evaluations. We can see the actual metrics of the model, and we can see how much the model actually gets correct. So we can see here that the model is actually only 50% accurate, which again might get a lot better, which definitely would get a lot better if we trained it for longer. But that means that the model on average looking at an image has a 50-50 chance of getting it correct. This is terrible when it comes to actual model training. But the idea here is the same, is that once you train this model longer, it will get a lot better. And all you need to do is just increase the number of, let's say, epochs, so the training iterations, just wait for that to finish, and at the end it will get a lot better. But you can see now that even with this very basic setup, the model does get okayish and does train and work as expected. So there you have it. In this episode, we built a model that can classify emotions from images very fairly quick. It was not as good as it can be because we didn't train it for long. You realize that it did get darker because I was spending a while here getting it to run and waiting for it to finish. So I'm not going to spend too much time training it longer. But you can see that the premise stays the same. All you have to do is train it for longer and then it will work. And this is basically how you could do a model that classifies cats and dogs or classifies anything else, and it would work the same exact way. But here we can see how models can interpret emotions, and this is basically how all other models work as well. Well, I hope this episode wasn't too technical for you. Let me know if you want to see more like this down in the comments. Let me know if you don't want to see any more like these, and I'll see you in the next episode.